If you have Lie group G, always contains a connected component to identity called G0. Okay, it always contains it. Then, but I showed you how to construct this G0, or at least the outline. Okay, that we follow this way. There exists a neighborhood of identity, call it U. Okay, it consists of all G epsilon, some number epsilon 0, such that G epsilon, so that G epsilon belongs to U means belongs to U. Okay. This I did not prove. This is U is called group germ. Okay. And in books you will see, even in physics books, this U is constructed using. We'll see what this exponential map is. I'll just write the phrase here. It involves solving differential equations. So I will non-linear differential equations, not trivial. Okay. So they invoke theorems on differential equations. So I will leave it here. Okay. But in explicit cases we can see it, what is happening. Okay. Then notice that I said last time U, okay, is well, here I have chosen, okay, by choice of epsilon, by choice of epsilon. The coordinate is chosen, so the origin is parameterized by the 0 conventionally. Okay. Now U is connected. That is okay, since okay, enough to show that is connected to E, to identity, right? Because then I can connect any 2 points via origin. Okay. Okay. Then we can connect G epsilon to G of epsilon prime via E. That is, if you have G epsilon here, G of epsilon prime here, E, can go from here to here and go backwards. So how do I do this? This is rather easy in this case. Okay. Now G of T epsilon, okay, because T0 and 1 is in U, because it's a like a ball, like open ball. Okay. All points less than epsilon are here. So T epsilon may be an n-dimensional vector. T is a parameter. Okay, is in U, and G of 0 is identity. G of 1, G of T, G of 0 is identity, and G of epsilon, okay, which is right this. G of T epsilon, T equal to 0 is identity, and G of T epsilon t equal to 1 is equal to my starting point g of epsilon. Okay, so I can draw feel like straight lines. Okay, then now G0 is a union on k u to the k. I want to show it is connected. No, it's also connected since G is in u to the k means G is of the form G of some epsilon 1 G epsilon k G epsilon I is in u, right, by definition. By the way, same G may occur in more than one u, that I don't, some more than one power of k, okay, that I don't care. And clearly G of t, which is G of, by definition, G of t epsilon 1 G t epsilon k, okay, 0 t 1, okay, connects, okay, G to E. So G0 is connected. Okay. So the importance of this is the following. Okay. So this the fact that I can the fact that okay, G0 is generated by U, okay, leads to, okay, study of G0, okay, from the small, from the neighborhood of identity. These are the Lie algebra methods. Okay. So this is the heart of the Lie algebra method. By way of comments, I can say the crucial theorem here is this, which I have not proved, is this thing that there is a neighborhood like this, okay, which is your group germ, which is not a trivial statement, this exponential map, okay.
You can always write an open set around there.
Yeah, but it is this statement here, that G and G inverse are the same thing, is not easy to prove, okay. You can find an open set, yeah, sure, but you don't know that the inverse is still there. And secondly, you don't know that you get the same thing when you take products, okay. The latter is given in Pontryagin. There is, it is very implausible that you are going to get two different groups by taking multiples. And for compact groups, I have to tell what is compact. But if the space group manifold is compact in technical sense, the number of things you have to take here is finite. It can be very large. But in the non-compact case, that is not the case. Okay. But you can do this. Okay. Let me give examples. Yeah. Okay. G0 tends to be U1 exponential I alpha. So you can choose U to be set of all things like this, okay, where epsilon is less than some epsilon 0. So these are the group here U1 is a circle as a manifold, and this is the, say, identity, and what I am doing here is take for U this thing, right. So if I go on multiplying it as a set, you will go on, you are going to get all possible angles by multiplication. They go on adding, and you will stop whatever if you pick here. After finite number of steps, you will cover the whole thing. That is because you are getting some cover. You can always cover a compact set by finite open cover. Okay, but anyway, there is a technical statement. B. Let's take So3. Here, as I told you yesterday, is a ball B3. This identity is E here, and you are identifying diametrically opposite points. So you can choose for U anything like this of radius epsilon. Okay, so you can choose for U all rotations of angle less than epsilon, but about around every axis. Okay, so U is consists of rotations by angles epsilon less than epsilon 0, okay, about every axis. Okay, so if I go on taking u to the k, okay, will then blow up this, then blow up this neighborhood. Okay, because you take one axis, you have got all rotations up to epsilon. Okay, you multiply again, you get up to 2 epsilon, 4 epsilon, you will go on like that, no? For this is exactly similar, okay, for around pick an axis, okay, U has axis n, U has rotations up to epsilon, okay. So clearly u squared u to the k has rotations up to k epsilon, okay. So you will go to the boundary, then okay, then you now choose all axes. Now vary axis. Okay. So then you get all possible rotations in the entire group. Okay. So the neighborhood of the origin somehow contains the information about the global group. Okay. This is very similar. Lie group, I told you that the composition function is analytic. That is, you know what is meant by analytic. The power series converges even on the real axis. On the real axis, you can tell when a function is analytic. If the power series converges on the real axis, okay, because then in some neighborhood you can continue it by analytic continuation, and you get a complex variable defined in that neighborhood. Okay, right? So you can tell whether some function is boundary value of an analytic function. Okay, That's the correct way to say. Okay. So here the composition function is real analytic. But you know that if you have a real analytic function, suppose I'm telling you that I have suppose I give you a power series expansion, say 0 to infinity a n x to the n, okay, for x less than some epsilon, and it converges, okay, converges absolutely, etc., etc. Okay. If it converges up to some point, it will converge absolutely beyond that, below that. Okay. Then by standard theorem, I think Cauchy or whatever it is, this can be made into an analytic function by writing z to the n, right? If it converges on the real, you can make it complex analytic in some small region. You can analytically continue it. But then by theorems on analytic continuation, the function is unique. Okay? The analytic continuation globally is unique. This is called the germ of the analytic function. Okay? It's unique, you can go on covering the whole plane. Okay? Then you might need branch cuts. You may have you come across branch cuts, branch points, square root of z. It may be that you have to enlarge the complex plane by going to Riemann sheets, okay, to complete the definition of the analytic function. But you can do it. There is a canonical way of doing it. Okay. There is the same thing that happens here for Lie groups, but there are additional structures here, yeah, namely the group property itself. So the possibilities are much more strict. Okay. Okay. But the idea is the same. Why this happens is the same. So now, yeah. Now I want to say, okay, a third way, okay, second way, okay, invariant integration. And character theory. The whole idea I is telling you is there are several ways to approach representation theory of Lie groups. One is this thing, okay, which leads you gradually to this Lie algebra theory, okay, and all the stuff which I will explain to you. The second is invariant integration. So here the inspiration comes. We saw that in finite groups. For finite groups, okay, we had the notion of invariant integration. Let me put integration within quotes. Which is, let's say, f, okay, the summation g, f of g, right? And which had the property that Sg f of gs. Here I wrote an integral in its, I don't mean integral in the standard sense or writing dx and integrating. The symbol is mapping the function linearly to complex numbers. That's what I mean. Okay. Then these things had this property, and this led to character theory. Then led to a whole bunch of results. Set of results, okay, including complete reducibility, okay, unitarity, of all IRS, right, in character theory. Okay, and structure of okay regular representations. It told us that by studying the regular representation I can get all representations. Okay, so this told us, I mean, these are intimately related statements. When we proved that the number of classes in a finite group is the number of irreducible representations, we were using character theory. Okay, similar things were being used here. Okay, all of this is coming just from here, this equation and Schur's lemma. This equation plus Schur's lemma. Schur's lemma is quite general. Okay, so the question is, can I do invariant integration for Lie groups? Okay, so the invariant integration is the statement. Okay, the following statement. Okay, theorem. What if, so let me put it this way. For Lie groups, say G0, what we will, so this consists of G of some parameters A. Okay. What we mean by invariant integration means, okay, an invariant integration means integration means okay, a measure. Well, measure we can just think in the simplest way. Let me call it d mu of g, which in local coordinates will be some phi of a. Let me see, what did I write here? Let me write dl r of g. Okay, I should say a left or right invariant measure means a measure rho Lr. Okay, so the form rho L of R of A dn of A, okay, which is such that left invariance measure, there are two in general. Okay, means that if I integrate on M or on G0 of any function d mu g f of g, so this integration is the usual thing. You put these local coordinates and integrate. Okay. I mean, this, of course the coordinates are not globally valid, but what happens is that these are all non-validities on some surfaces of lower dimension, so integral they will wash away. Okay, I will make more remarks on how to write them nicely. Okay. Huh? Rho L is multiplying is a Jacobian factor. I will give you the Jacobian factor. So this is left invariant is FL, okay, and it is left invariant is equal to this one d mu L of G times say f of any left at G for all H. Okay. So you to do the integral, you will put this here and you have to rewrite this in local coordinates and then integrate in the usual sense. looks very awkward. It is in fact awkward in local coordinates, but there are global formulae which I will give. Okay. But I will give you the answer. Okay. Right invariance means similarly, so left is this way. Okay. So that will be G0 d mu r of G f of G. So all f or smooth f, of course. Just like there, f is all h and all f. So this is equal to d mu r of G f of gh. In general, I will tell you when they are equal. Rho L is not equal to rho R, but they exist for a very large class of groups. The cases we consider, in fact, they will be equal. I will tell you the conditions where they are equal. Okay. So what is the formula? Okay. So I will give you a formula for rho L rho R. Okay. If say G of A, G of B is G of A times G of B is G of phi AB, no, it is, you have to multiply it, the log G of phi is an argument. Okay. So it's giving you the coordinates of the composite operator. Okay. Then rho L of A is, yeah, so inverse of the determinant is equal to determinant of, if phi is a multi-component, no, phi rho, okay, AB or D B sigma, this matrix evaluated at b equal to 0 inverted. Okay. It's a Jacobian, it is a thing when you change the coordinates, okay, you will get a Jacobian, but this will also transform in a particular way and they will cancel. Okay. Likewise rho R of A, well, let me call it rho R of B, will be determinant of d phi rho of AB or dA sigma, okay, A equal to 0 inverse, this inverse. Okay. The proof for this is a homework. Okay. Proof is a homework. It is not difficult. You have to look at this formula and differentiate and get identities for the determinants. Okay. Then you will find the answer here, which I have given you. So I have given the thing as a homework, but this you can always do. Okay. Now, this looks complicated because this is like introducing Euler angles, but this shows the existence of these measures. Okay. Normally you don't use this formula. This formula is, by the way, in Berner's book and some other books also. But if you know differential forms, do you know differential forms? Huh? Little. Then I can write down the formula right away. Okay. It's very easy, and then you can say, oh, of course, okay, use, you know. Okay. Let me state the properties of this. and maybe I come back to differential forms. You can give, let me show some examples. Okay.
You can write on the formula.
I'll come back to that. Okay. I'll come back. First let me show some properties of Lie groups which follow from these meshes. Then finally I give you formulae. Some of these formulae, by the way, are used in quantum field theory. Instantons. If people have dealt with instanton physics, it is used. Of course, we use it all the time in when you do group theory, like SU3. Okay. When you have to deal with invariant functions on, when you deal with functions on SU3. For example, when you do Feynman graphs, there are so-called large n expansions and so on, where these things come up. But never mind. Okay. Okay. First is the following. Let's write remarks. These meshes are unique up to overall constants. This is an only non-uniqueness you can find. Okay. The reason is that if you write anything else, basically you have to prove, what will happen is if you try writing anything else, you can only with this multiply by some function on the group. Okay. But then if you apply the invariance property, you will end up by proving that this what you put here is a constant on the group. Okay. By using this formula. Okay. Because that it will let this, if you insert things here, you cannot change. It is, you put this formula has to hold. But if the damn thing you put here changes, you will get extra factors here which have to stay the same. Okay. So for this reason, these are unique. Okay. This is important. Secondly, the following statement is true. Okay. 2. D mu LR are actually meshes. That is that is, if f is positive, f is non-negative, this integral d mu LR f is non-negative, and 0 if and only if f equal to 0. Well, in the measure theoretic sense. Okay. So it's actually a measure, is a volume. Okay. Doesn't change sign and suddenly become 0 in some region. That kind of thing does not happen. It's because of the invariance. If it is non-zero in some region, because of the invariance, you can translate the non-zero region all over the place. The damn thing doesn't change. Okay. So it is homogeneous. What you are attaching to as a like translate dx on a line. Okay. Dx on a translationally invariant way of integrating. Suppose I take a line, I write something like d mu of x for integration, and I require that this is invariant. Okay. Here also, what this means, this equation here, okay, can be written as d mu L G0G Hg is d mu L of G, and likewise I can say d mu L R of GH is d mu R G. Okay. There is, if you change variables of integration like this, nothing happens. Okay. So if suppose I am given this equation on an ordinary line, the only possibility for this d mu x is some f of x dx, right? There is nothing, because there is only local coordinate is only possible, but this says f is a constant. Right? And this constant all over, and the volume I give to some small region where this thing is positive is the same volume I will get for every translated region. Right? So it cannot vanish unless it vanishes in the starting interval, okay, which it does not by construction. Okay. So there is a certain homogeneity. So that from that you have this result here. It is actually a measure. So that means, so this is important. So consider two Hilbert spaces HL. So I give you scalar product, okay. L is right, which is d mu L of G alpha bar of G beta of G, okay, and I write HR, which is alpha beta right, which is d mu R of G alpha bar of G beta of G. Okay. So this is my scalar product, and what I can say is that on HL, HR, the left right regular representation is unitary. Because the left regular representation translates G on the left. If you remember U of H, so in the left regular representation UL of H F at G was F of G, H inverse G, right? And the right one was on the other side. Okay, so it is unitary, because if I do the same thing on the left, it will cancel out. So these are unitary representations. Okay, this is very important. When you do partial analysis, so when you separate variables in Schrodinger equation, you are using this kind of thing. Okay, underlying all that activity is this result here. Okay, okay, and we'll come back to this when we go into representation theory more. Okay, but less obvious are the following things. Okay, where was I? This was 3, right? 2, 3. Because a group G0 is compact if and only if, say, d mu L of G on G0, which I'll call V, is less than infinity. So you don't need topology. Okay, you can integrate, and the volume is finite, the group is compact. Okay. In this case, then, okay, we can also say d mu L of G is d mu R of G up to constant, up to constants. So in this case, the left and right invariant measures are the same. Okay. Okay. This result here, okay, this is true also for, let me see, yeah, this result is also true for abelian and simple groups, simple and abelian. Yeah. Simple, for example, it is true also for Lorentz group, but Lorentz group is not compact. It's also true for the real line. Okay. So there something else is happening. Okay. All these are unified by this formula, which I will tell you now. By this formula with differential forms. Okay. Which
You're using differential concepts to talk about compactness, but compactness is usually introduced in the topological.
yeah.
How are the equivalent?
This is a maths question which it is known that many of the results you get using differential structures persist when you go into, when you don't even bother about that. Okay. Why this I don't know enough, I don't know enough math to be able to answer that. Okay. You are asking, if I am only looking at topological concepts, why should I put, if I prove something with differential, why should it persist in the topological context? Okay. I think the differential structure has to be compatible with the topological structure.
How the two definitions are equivalent?
The definition is the same. Okay. That is, compactness in the topological thing is what is used here, okay, in proving this result. So on the compact space, if you put a volume form, it will be having this property that when you integrate you get finite. Okay. Why these two things are coinciding, I do not know. This happens all over the place. Okay. I don't know how to say it in a good way. I know by calculation, but I don't know. Vanga. I can't. I know this Poincare conjecture which was proved. Okay, you have heard about the Poincare conjecture, which was proved very recently, Perelman and so on. It uses the all those conjectures are purely topological state based. Poincare conjecture is that the only closed, that is compact boundaryless 3 manifold, which is simply connected, is 3 sphere. That is a statement. Okay. It's purely a topological statement. Okay. But it is proved by what they call Ricci flows, some general relativity ideas, okay, which came from quantum field theory using renormalization group. Okay. So completely different ideas coming from, actually if you look in Perelman, he will say he got it from work on quantum field theory. Okay. Okay. So then he applies. So why? But there is a background which I don't know. So now, yeah. So let me look at examples. Then we will look at how to write it in a good way. Okay. Examples. So let me look at the 1 plus 1 Lorentz group. Let me work it out. Here, so this is 1 plus 1. Okay. So very often people write this as SO11. Okay. The metric is 1 minus 1. Yeah, right. The lecture, there is no lecture here. Okay. So the elements of this group, okay, will consist of g of theta. This is normally written as cos theta, shin theta, shin theta, cos theta. Hyperbolic theta, and you can check that g of theta 1, g of theta 2 is g of theta 1 plus theta 2. Okay. This theta is called rapidity variable in physics. This thing is used in the analysis of, you may know that when you have say you have two collisions, say PP bar in LHC, or maybe originally it was electron positron at very high energies, then near the forward direction you get jets. Things are highly collimated and they go forward. You get jets, okay, going very rapidly. Okay. So for the analysis of the jets, this is almost linear. It is going almost in the same day, highly collimated things. Okay. So the analysis of these jets, where they come from and so on, this variable is used, okay, for the jet phenomenology and what they call deep inelastic collisions. Okay. So this variable is well known, but for us the important thing is this means phi of theta 1, theta 2, this theta 1 plus theta 2. So we can see this is simply addition. So this thing here, d phi theta 1 theta 2 or d theta 2, there is no determinant, theta 2 equal to 0 is equal to theta 1 is equal to 1. This is also the true for d phi or d theta 1 of theta 1 theta 2. Here I set theta 1 equal to 0. Okay. So you can say that rho L of theta is equal to rho R of theta, and you can set it equal to 1. Okay. So the left and right invariant measures are the same, okay, but this comes from the fact that this group is abelian. Abelian means it commutes. You remember we defined this. But the group volume d theta, here theta can be any value from minus infinity to plus infinity, is infinite. So group non-compact. In contrast, if I look at u1, which is exponential I theta, but here theta is between 0 and 2 pi. But notice that theta is not a global coordinate, because 0 and 2 pi are giving the same point. No? But for integration who cares? You remove the point. It doesn't make any difference because manifolds of lower dimension don't make any contribution to integration. Okay? So this is not global coordinate, but doesn't matter. But here, since the local coordinate is theta, okay, since this equation is true, theta 1 plus theta 2, again rho L of theta is rho r of theta is equal to 1. Of course group is abelian, but the group volume is 0 to 2 pi d theta is less than infinity, or U1 is compact. And finally, okay, let me write down the answer instead of trying to make it plausible. Let's look at the So3 group. Here, from rigid body study, let me in classical mechanics, okay, we know that R in So3 can be written as R of, okay, phi theta, let me write it alpha, okay, phi is 0 to 2 pi, theta is pi to 0, right, and alpha is 2 pi to 0. Okay. This is business. Alpha is rotation around third axis. Theta, how does it go? Is a rotation around second axis, if I remember correctly, and this last one is again rotation around third axis. Okay. So you write the full rotation as a product of 3 rotations. Okay. Then let's write d mu L of for the So3, okay, Gr, I give you the answer, d phi d cos theta d alpha. I am not deriving it. There are trick ways of deriving it. You will notice that these two factors, these are just the volume form on the two sphere, and this is the missing thing, the rotation which leaves a point on the sphere fixed. Okay. So, but anyway, what I want to compute is the volume, okay, which in this case is integral of this form, which is from d phi it is 2 pi, d cos theta is minus 1 to plus 1, 2, and this gives you another 2 pi, so 8 pi squared, which is less than infinity. So So3 is compact, and d mu L is equal to d mu R. In the book I have given some plausibility arguments for this. Okay, why this formula I have written down is reasonable. Okay, but let me I won't get time to finish this, but
There's different left and right measures, and both of them giving different answers to the volume of the group.
you will not get, you will get, if it is finite, you will get always the same answer. It's a theorem.
But the measures themselves needn't be
Up to overall constants. Okay. I mean, you can multiply it by 20. Okay. That I cannot control. No? So you have to you can normalize them, but so that if you normalize them on the unity, they will give the same value for integration on any function. Yeah. Okay. Now, what I will do next time is give you a rapid course on differential forms. That is, what do I mean by things like dx1 dash dx2? I mean, I want to give you at least the rules of integration with differential forms, because these formulae all look extremely simple if I use differential forms. Okay? You don't need local coordinates or anything, and it is used in these papers of the Russians when they were discussing instantons. Old papers on instanton physics, which has a lot of physical consequences, you see this formula used constantly. Of course, those fellows were coming from the St. Petersburg school. Okay, St. Peter, no, at that time called Leningrad school. Okay, all these big shots were there. Eshetikhin, Fadeev, Belavin. Okay, and they were also doing physics, and naturally they were using such things. But I want to tell you this. But if you want a very rapid thing, you can look in this first volume of Gelfand and Shidov. Generalized functions. Volume 1. Okay. There is a very short section on how to manipulate with differential forms. Okay. Basically, they give you rules on how to manipulate it. Okay. Without going into the what do they mean, where they come from in differential geometry, they just give rules. So if you give a formula, you can write it in terms of differential forms, and you can jolly well go ahead. You can change variables. The advantage is change of variables won't make any difference. Okay, you'll automatically pick up the right Jacobians. All these things will be taken care of. Okay. So they are given the formula, and I'll try to recall to you the formula and write this formulae for all finite dimensional matrix groups in a nice way. Okay. Then you will see that for all these things, left and right invariant measures are the same. Okay. And it's coming from because of the fact that the trace is 0. Some trace is cyclically invariant. Trace is cyclicity property. No? So you have a cyclic trace which you can define, and the origin of this identity for all the finite dimensional matrix groups is this. Okay? And for compact groups, So3, SUN, I write a formula. Okay? And the formula is very simple. And if you are anxious to write it in local coordinates, you can do it. It will take you maybe 3 weeks, but you can do it. Okay? But if you don't want to do it, you don't have to do it. Okay? So I'll do that next time.